Swayam Prabha. Digital India. Educated India.
Hello, today I'll continue the discussion on Euler equation for turbomachinery. The content of the lecture today is illustrations of Euler equation, radial flow turbines, then I would go to axial flow machines, and here I'll discuss on pump or compressors and turbine. I'd initiate the discussion today with a radial flow turbine. I've sketched here a radial flow turbine which is inward flow. Please note that the compressor was outward flow, but a turbine is inward flow here because of the fact that a radial flow machine, particularly a turbine which is inward flow, is stable. Why? Because an increase of speed would tend to increase the centrifugal force, and in turn it will decrease the flow rate. Thus, please remember, a inward flow turbine is a stable machine, while an outer flow turbine is unstable. I have sketched here the velocity triangles. This is the inlet velocity triangle. So U1 plus W1 is equal to C1. And radial component is denoted by CR1, which will be related to mass flow rate of the machines. At exit W2, U2 would be equal to C2. And the radial component is CR2. And tangential component of C2 is C theta 2. And similarly, tangential component of C1 at inlet is C theta 1. I have illustrated the direction of rotations. You note that in a turbine, C2 will be less than C1. C1 will bring the kinetic energy to rotate the machines. So it's in the direction of rotation is in the direction of C1. Particularly also note that your W1 and W2 would follow the blade angle, and W2 will accelerate. So the magnitude of W2 will be higher than W1. So considering the direction of rotation, this is a backward curve impaler, and this is a forward curve impaler, the direction of rotation being the same as this. So look here, C theta 1 is much larger than for a backward curve machines. So obviously forward curve impaler will be associated with more work transfer than a backward curve impaler. I have written here what I have stated earlier, that for a turbine, relative velocity will accelerate. That is why W2 is greater than W1, and thereby P2 will be less than P1. Hence, the exit pressure would be less than or equal to the inlet pressure. And the Euler work is given by U1 C theta 1 minus U2 into C theta 2, which becomes maximum when C theta 2 is equal to 0. Now, if we consider for incompressible flow, suppose a turbine, a water turbine, and finally water will be collected by a draft tube, and through the draft tube the water is thrown to the reservoir, and the efficiency of the draft tube increases if some swirl exists. That's why often designer keeps some swirls at the outlet. Now I'll go to the axial flow machines. I have shown you a sketch of an axial flow machines indicating that several stages, and as I have drawn the picture, this is an axial flow compressor. You look, the annulus area decreases because of increase of pressure, and you can find the series of rotor blade followed by the stator blade, again rotor blade followed by a stator blade. The combination of a rotor and stator is called a stage, and particularly the first row of rotor is called inlet guide vane. Please follow the pointer. If I take a circumferential section and stretch on a plane of paper as I have shown here, you will find array of blades. The first array here is nothing but IGV, that is inlet guide vane, followed by the rotor and then stator. The flow will turn through this IGV, rotor and stator, but rotor rotates about the axis, whereas IGV and stator are stationary component. Now there will be force on the stator and IGV because of deflection of fluid as it passes through the stator, but there will be no work producing component as they are stationary. However, in the rotor, as they are rotating, there will be some work producing component because torque multiplied by angular speed, so omega is nothing but work. Now, then what is the function of IGV, inlet guide vane? Look, I have shown you the throat area. By tilting the IGV, I can increase or decrease the effective area through which the fluid passes, and thus I can control the mass flow rate. So function of IGV is to control the flow, and by the combination of stator and rotor we guide the flow properly to pass through the rotor, and the combination of stator and rotor is called a stage. I have written here the combination of rotor and stator is called a stage. Please note that for a compressor, stage is defined by the combination of a rotor and stator, Whether for a turbine, it is defined as stator plus rotor. And when the pressure rise occur through several stages, the machine is called multi-stage machines. Now through this sketch, I have illustrated how the lift and drag develops on blades. Please note that as the flow passes through series of blades, the fluid deflects, and because of this deflection, because of the turning of the flow, there will be circulation developed on the blade, and thereby the lift generates. You can think also that fluid flow will decelerate on one side, whether in other side fluid flow will accelerate. And because of acceleration and deceleration of fluid flow, one side pressure will be higher with respect to the other side. So where the pressure will be higher, we call is a pressure side of the blade, and where the pressure is relatively lower, we call it as a suction side of the blade. And I have shown here, which is called chord, and this is the throat, which is the minimum perpendicular distance between the two blades. And this distance is called the pitch. So pitch, chord, throat, they are very important geometric parameter. Now I have explained here how lift developed on the blade surface, and I have written here just to remind you, because of turning of flow through the blade, there will be lift. Furthermore, for viscous flow, the boundary layer would develop on the blade surface, and because of this development or formation of boundary layer on the blade surface, a weight will be developed behind the blade. This is a sketches which illustrates boundary layer formation and weight development behind the blade. And because of this boundary layer formation and the mixing of weight behind the blade, there will be a loss. Thus, drag will develop on the blade surface. So I have written here that occur due to the growth of boundary layer over the aerofoil surface. Through a sketch, I have shown here surface pressure distribution on the blade. This is the pressure distribution on the pressure side, and this is the pressure distribution on the suction side. From the pressure distribution, one can appreciate that flow decelerates on the pressure surface while the flow accelerates in the first half of the blade and then diffuse in the second half of the blade. Therefore, the second half of the blade experience an adverse pressure gradients. And look, if we increase the angle of attack tells you the direction of the flow with respect to the blade. Now, if we increase the angle of attack, you can produce higher adverse pressure gradient in the second half of the blade. And because of this high adverse pressure gradients, often for high angle of attack, the flow separates on the suction surface, forming a separation bubble. This separation of flow on the suction surface is not desirable. That would increase the losses. I have also indicated here now the losses and the combination of loss occurs because of formation of boundary layer on the blade surface, that's called the profile loss, plus loss because of mixings of weight behind the blade, that's called mixing loss. And furthermore, the boundary layer developed on the annulus area of the turbine or compressor, that's called annulus loss. Apart from that, there are secondary flow losses that I'll discuss later. So I have written a sentence here. The losses are because of profile loss, mixing loss, annulus loss, and secondary flow loss. Now, as a designer, I'll try to optimize lift to drag coefficient. That's always my goal. So here I have written here that always a designer tries to optimize the ratio of lift and drag coefficient. I have considered here an axial compressor or pump, as I have shown in the figure, a rotor, and for simplicity I have considered that steam surface is axisymmetric as entry and exit, and there will be no radial seep of steam surface as the flow passes through the impeller. And if we neglect the radial seep, then U2 must be equal to U1, where U is the blade speed. Further, I have considered a mean stream surface. So the section I have shown in this figure, and if I stretch that section on a plane of paper, I'll get array of blades. So this is the array of rotor blades, which are aerofoil constructions. And I have drawn the inlet and exit velocity triangle. As before, I like to tell you that W1 plus U1 would be equal to C1, and this would be a vector addition. For an axial flow machines, I have defined flow angle with respect to axial direction, and beta is meant for relative flow angle, alpha is absolute flow angle, 1 is refers to as inlet and 2 as exit. So please note that here beta 1, alpha 1, and similarly beta 2, alpha 2. Further, what I like to tell you, please note the direction of the rotations. So this surface will be positive surface and this will be the negative surface, which I call pressure surface and the suction surface. And now the direction of rotation is such, it will tell you that you will have to supply energy from the outside, being a compressor. Further, as it is a compressor, inlet flow has to decelerate as it will pass through the impeller. So W2 is less than W1, and hence P2 will be greater than P1. And please note that here beta 2 will be less than beta 1 because of turning of the flow. Furthermore, here I have considered the two streamlines, which is the relative streamlines passing through the mid plane between two neighboring blades. And I have considered A1 and A2 be the nominal distance between these two streamlines. And these are the relative streamlines. Now I may consider that W1, A1 must be equal to W2 into A2. Since A2, W2 is less than W1, A2 must be greater than A1, and therefore the relative streamlines or relative stream surface will diverge as they will pass through the impeders. This is in nutshell the velocity triangle, and I request you to practice the velocity triangle, and through the velocity triangle you can evaluate now the work output. Now for a compressor del P0, considering an incompressible flow can be given as eta A0 into U2 C theta 2 minus U1 C theta 1, or del H is equal to eta H into U2 C theta 2 minus U1 C theta 1 divided by G, where del H is equal to head rise per stage. Now similarly, let's take a turbine, and I have drawn here the blade profile and the velocity triangle as inlet and exit. The notation is same as before. I've also taken the two mean streamlines passing through the impeller passage. Here you note that flow will accelerate and will pass through the impeller, and so W2 here would be greater than W1, and hence P2 will be less than P1, and thus here I have shown A2 will be less than A1. Quite opposite things appearing over here. And look, I have maintained the direction of rotation is same as before. Now you will find the pressure and suction surface will be aligned in such a way that pressure surface will dictate the rotation. Thereby you can appreciate that you will get work output from a turbine. Now note the significant difference here. Not only W2 is greater than W1 because flow will accelerate, but B2 will be higher than beta 1. Beta 2 will be higher than beta 1 because of turning of the flow. And alpha 2 will be less than alpha 1. So please note the different features appearing here because of turbine. Thus, for a turbine considering incompressible flow, we can express del P0 equal to rho into U1 C theta 1 minus U2 C theta 2 divided by eta H. Eta H being the hydraulic efficiency, and del P0 is the pressure drop in a stage. Similarly, I can write del H, that is head drop in a stage, is equal to U1 C theta 1 minus U2 C theta 2 divided by eta H into G. We often use the relation which is an empirical relation, the Cz by U. U is the blade speed. We keep that in a limit 0.3 to 0.5. I like to tell you one very important point, that for a compressor, the flow decelerates. Thus, the boundary layer on the blade surface grows against an adverse pressure gradient. And so there will be a chance of separation. On the contrary, the relative flow accelerates for a turbine, so there will be favorable pressure gradients. Thus, the boundary layer growing against favorable pressure gradients is less amenable to separation. That's why the efficiency of a turbine is often more than that of compressors. Considering the fact, more care needs to be taken to design a compressor. Thank you for listening.